earlier video about linear algebra, we looked at the Gram-Schmidt process of finding an orthogonal basis for a set of vectors that spans the same space as our vectors but are perpendicular. We were specifically trying to find a set of perpendicular vectors because a perpendicular direction creates the shortest distance. So once you have an orthogonal set of vectors that span a certain space, you can find the best approximation to that space using those orthogonal vectors. So here we have some vectors, 2, 8, 3, and 1, 1, 4, and they are not perpendicular to each other and they span some plane in R3. If you do find an orthogonal basis, you can include one of the vectors. So we included 1, 1, 4 as one of the vectors in that basis set. And then we found another vector to form an orthogonal basis, and that vector was 7/9, 61/9, -17/9. And that vector is right here. It's a little hard to see in our graphic here, but 1, 1, 4 and that vector are perpendicular to each other, and notice they're in the same plane as 2, 8, 3. We've got another vector that we're going to call y, and y has components -2, 1, 6, and it is not in that plane. So it is not in the span of 1, 1, 4, 2, 8, 3, or 1, 1, 4 and this perpendicular vector that spans the same space. But what if we wanted to approximate y as best we could but still stay in our homeland of this span, of this plane, of this spanned space by those vectors? Well, then we would be finding the orthogonal projection. The idea is that you add the projection of y onto each of the vectors that span your space. And we're going to use the perpendicular vectors, the orthogonal basis vectors. And you need to do that. You need to use the orthogonal basis vectors in order to find this best approximation. So A and that vector v2 formed our orthogonal basis. And by the way, again, when you find a projection, what you're doing is you're dotting a vector with the other vector, and then you divide by the dot product of the vector you're projecting onto, and that gives you a number. That scalar then multiplies the vector whose direction you're trying to project onto. So that's what we have here in terms of y dotted with A and y dotted with v2. So y dot A is 23. If I take -2 times 1 and I add 1 times 1 and I add 6 times 4, I will get 23. Now v is a little bit messier, and so y dotted with v2 is -55/9. A dotted with itself, which by the way again is the square of the length of A, is 18, and v2 dotted with itself is 451/9. Plugging those values in, y dotted with A was 23, A dotted with itself was 18, and then we're multiplying vector A by that scalar. And then v2 dotted with y was -55/9, and v2 dotted with itself was 451/9, but you can clean that up, divide out the 9, and then divide by 11, and we get an equivalent fraction of -5/41. So -5/41 is the scalar that I multiply v2 by. And then I add these two projections together, and again it's a little bit messy fraction arithmetic, but after I clean it up I get 97/82 for component 1, 37/82 for component 2, and 219/41 for component 3. If you then want to see that vector, we've plotted that vector, and it's the yellow vector here, and I know the components are not showing up very well, but they are the same components that we found earlier. So 97 over 82, 37 over 82, and 219 over 41 are those numbers. But I was more interested in just showing that that vector does fall in the plane of A and V2, and again that vector B. Again, we found V2 because we were trying to span the same space as the blue vector and the red vector. So the yellow vector, which is our approximation to Y in this plane, you can see does fall in this plane. And then notice it's falling directly underneath the original Y. So basically it's like the shadow of vector Y cast onto this plane spanned by those other vectors. You might be interested in the error, and so the error is literally how far apart are the terminal points of Y and Y hat. Again, Y hat is the notation that's often used for an approximation or a prediction. So we're finding the distance between the two terminal points, and we follow the distance formula like we learned in college algebra class, and we find the difference of the X, or the first component, squared. We find the difference of the Y, or the second component, squared. We find the difference of the Z, or the third component, squared. And here's some decimal approximations of those differences, and we get a distance of approximately 3.296. So this tip is approximately 3.296 from the plane, and that's measured from the terminal point of that yellow vector. We were able to actually draw some graphs for R3, but the idea stays the same no matter what dimension you're in. So we could be in a higher dimension, R4, and we could have these three vectors, A, B, and C, which are not perpendicular to each other, and they span some three-dimensional space in R4. You can find an orthogonal projection that spans that same space. Again, we did that in an earlier video. And so V1, V2, and V3 are the orthogonal basis that spans the same space as these three vectors, and these vectors are perpendicular. This vector 3, 5, 17, -6 does not fall in that spanned space. If you wanted to check it, you could set up a system of equations assuming that there's some linear combination of these three vectors that will give you that vector. But when you set up that system of equations and you row reduce, this is the row reduced matrix, and X has a solution of 0, Y 0, Z 0, but when you go to find the fourth component, you get a statement that says 0 has to be 1, but 0 can't be 1, so there's an inconsistency. There is no solution. Because there's no solution, this vector is not in the span of those three vectors. But we want to approximate it in the span. So we're going to follow the same idea that we did earlier. We're going to find the projection of Y onto the other vectors that form the span. So onto V1, onto V2, and onto V3. For our three vectors here, notice they're combinations of 1 and 3, and so they all actually have dot product equal to 12. So V1.V1 is 12, V2.V2 is 12, V3.V3 is 12. So all of the dot products in the denominator is going to be 12. And then Y dotted with V1 is 23, Y dotted with V2 is 37, Y dotted with V3 is 49. Again, you're dotting this vector with each of these. Okay, so 3 times -1 plus 5 times 3 plus 17 times 1 plus -6 times 1. That would be the dot of Y with V1. So forming our projections, we have 23 over 12 multiplies V1, 37 over 12 multiplies V2, 49 over 12 multiplies V3, and if I carefully do that arithmetic, adding -23/12 to 3 times 37 twelfths to negative 49 twelfths, I get 13 fourths. And 3 times 23 twelfths added to 37 twelfths, subtracting 49 twelfths gives me 19 fourths. 23 twelfths plus 37 twelfths plus 3 times 49 twelfths gives me 69 fourths. And lastly, 23 twelfths minus 37 twelfths minus 49 twelfths gives me negative 21 fourths. These are relatively clean decimals, so 3.25, 4.75, 17.25, negative 5.25. It's kind of worthwhile to look at that because, again, you're trying to approximate this vector. So notice 3.25 is pretty close to 3, 4.75 is pretty close to 5, 17.25 is pretty close to 17, negative 5.25 is fairly close to negative 6. The error then is the difference between the original y and our approximation. So subtract the first component squared and then square, subtract the second components and then square, subtract the third components and then square, etc. And we get an error of approximately 0.8660. So that's a little review about what it means to find an orthogonal projection. This is using this kind of straightforward definition of what a projection is. There is a nice application using matrices that we will look at in another video. And that process is called using the normal equations.